Okay, thank you very much. It's really a great pleasure and honor to be here at this amazing mathematics center. So the title of this mini course is Qualitative Theory of the Poisson Boundary. So what I'm going to do is that I'm going to introduce and describe the notion of the Poisson boundary. I will actually do it in full generality. Then I will look in more detail at the Poisson boundaries of random walks on groups, and the reason why it is called qualitative theory, because there is a quantitative theory which has been quite developed by now, which talks about the entropy, rate of escape, Hausdorff dimension, and various interrelations between these quantities, which was already, as far as I understand, mentioned by Peter in his series of talks last week, and which will, as far as, again, I understand, will be mentioned this week in talks by Sebastian. But I just want to talk about the qualitative theory, namely no numerical quantities will be involved, and I will just discuss how the Poisson boundary reflects certain basic properties of underlying groups. And there, well, let me announce in more detail, so which properties I'm talking about. One of these properties is amenability, and a characterization of amenability in terms of the Poisson boundary had been known now for almost 40 years. But just last year, in a really striking new result written by 4 mathematicians, so not sure whether I can do it in the alphabetic order, Omer Tammuz, Yair Hartman, and Joshua Frisch, and Vahidi Ferdowsi, who actually completely characterized the other end of this problem, namely we described the groups for which the Poisson boundary is always trivial. And I'm going to talk about this very new result and about its even more recent ramifications obtained in my joint work with Anna Eschler. But let me just begin with the general notion of the Poisson boundary. And actually, this year is 2019, next year will be 2020, and it will be precisely 200 years since Simeon Poisson published, let's say, the first draft of what we now call the Poisson boundary in Journal de l'École Polytechnique. Actually, the way Poisson obtained this formula is quite different from how we looked at it nowadays. He did it as an application of the newly discovered at the time Fourier series, and he noted that given a certain nice function, you can relate its boundary values on the unit disk with the values of this function inside, or you can express the values of this function inside the unit disk in terms of its boundary values. Talking about history, then of course one should mention the famous Cauchy integral, which provides yet another point of view at the Poisson boundary. But since this is a meeting on the negative curvature and what's the official title? And probability. Then I will actually use a probabilistic and negatively curved interpretation of the Poisson boundary, which is the following. So let me do it first in the classical form. So suppose we are given D is the unit disk, then the boundary is the unit circle. And then we're looking at functions. Which are bounded and harmonic inside the circle. So what harmonic means in the classical description, harmonic means that Laplacian of our function vanishes. So Laplacian is the sum of the partial derivatives with respect to each variable. Okay, so suppose that we have such a function. We can even assume that it is continuous up to the boundary. And then it turns out that the values of this function inside are entirely determined by its boundary values, which, in other words, means that our function is the solution of the Dirichlet problem with the boundary values on the circle. Okay, so how does one recover this function from its boundary values? So here, one can do it in several different ways as well. So one can, let's say from the point of view of the functional analysis, do the following. So we have our boundary values on the boundary circle. And then, since we know that the Dirichlet problem is solvable, it means that our function extends uniquely and continuously inside. And then let's take a point inside. We therefore, for any point, we have the following functional. We take the boundary values and then we assign to these boundary values the value of the harmonic extension of our function at a given point x. This is linear functional, the space of all continuous functions. And therefore, as such, we have a description of all linear functionals on the continuous functions on a compact set, and these linear functionals are precisely given by integration of our boundary functions with respect to measures. Therefore, it means that for any point inside our unit circle, we have the associated measure on the boundary, have the associated probability measure on the boundary, and this is what is called the harmonic measure. The harmonic measure, sometimes one says, so one has to take into account the fact that this harmonic measure depends on points inside. So let's say with the pole at the point x. Okay, so now the question is, it's still pretty abstract. How do we describe these harmonic measures? How do we describe these harmonic measures? And here one can use the fact that our unit disk comes equipped with the group of all conformal automorphisms. And harmonicity is preserved by conformal maps. That's a very fundamental fact. And therefore, it means the following, that instead of talking about arbitrary points inside the unit disk, we can just consider the geometrical center of the unit disk, figure out what the harmonic measure for this point is, and then apply an appropriate conformal transformation which maps the center of the disk to this point x. Now, once again, from these symmetry considerations, if we are now looking at the harmonic measure associated with the center of the disk, then since everything here is invariant with respect to the group of the conformal transformations, this measure also has to be invariant. And who are the conformal transformations which preserve the center of the unit disk? That's the rotations. And therefore, our harmonic measure of the center of the disk, has to be rotationally invariant. And of course, the only rotationally invariant measure on the circle is just, well, the usual Lebesgue measure. Just the usual Lebesgue measure. So, in other words, we can now say that the harmonic measure nu x is the unique measure on the boundary disk, invariant with respect to the conformal rotations around this point x. Okay, so this was a conformal description of the harmonic measure, and now one can, well, since there is the word probability was mentioned, now one can pass to, and negatively curved manifolds were mentioned, now one can pass to a description of the Poisson formula in probabilistic terms involving negatively curved manifolds. Namely, here I have been talking about the unit disk, but of course, everyone knows that the unit disk also can be considered as a model or the Poincare model of the hyperbolic plane, the hyperbolic plane. So now the interior of the unit disk can be identified with the hyperbolic plane, can be identified with the hyperbolic plane, and the boundary of the unit disk can be identified with the circle at infinity of the hyperbolic plane. Well, let's call it the absolute of the hyperbolic plane. Okay, so now in this description, in this interpretation, we are talking about the following situation. The advantage of this description is actually that when talking about the unit disk, we were assuming too much. Our structure was redundant. Namely, here we had a fixed point, the center of the unit disk. And the more doesn't necessarily mean the better. Because in this situation, if we want to understand the inherent structure of what we're doing, we don't have to fix any points. We should really consider the following situation. We're dealing just with our state space, and none of the points is better than another one. So, here, if we take an arbitrary point of the hyperbolic plane, then one can look at the all the symmetries. Let me denote it by G. X is the of the group of all the isometries of our hyperbolic plane, which fix our point x. So in metric terms, these are just, well, the rotations, the isometries which fix a given point x. Okay? And then in these terms, the measure nu x is the measure on the boundary of hyperbolic plane, which is invariant with respect to these rotations. So everything is very natural and very symmetric. We take our hyperbolic plane, then once we have a point, there is a natural way to assign to this a point a measure on the boundary. So in other words, we embed our manifold, our hyperbolic plane, we embed it into the measures on the geometrical boundary, Well, one can still talk about harmonicity in this situation, once again, because the Laplacian is conformally invariant. And when passing from a hyperbolic plane to the unit disk, we are doing conformal transformations. So what we now have is the following theorem. The classical Poisson formula. Okay, let me denote by H infinity the space of all bounded harmonic functions on the hyperbolic plane. This is a Banach space endowed with the usual supremum norm. Okay? And then the claim is the following, that this space of bounded harmonic function is isometrically isomorphic to the space of all bounded measurable functions on the boundary. Okay, so here I have specified the boundary circle. That's where the boundary values are supposed to live. And then, since I'm writing L infinity, I have to specify measure. But instead of a measure, I will be talking about a measure class. Since I'm looking at the space L infinity, it's precisely the same. So I will be talking just about the class of all harmonic measures, which I denote like this. So these measures are actually all pairwise equivalent. Okay, so now how does one establish this isomorphism? How does one establish the Poisson formula? In the following way. So the value of a harmonic function at a point x is the integral of the associated function on the boundary against the corresponding harmonic measure. So that's the most invariant way to write the Poisson formula. However, usually one, or let's say in the analysis, when one talks about the Poisson formula, one means integration with respect to the Poisson kernel. So let me write it in more classical way. So here we have the integral of the boundary values with respect to the associated boundary measure. And now what one does is that instead of varying the measures with respect to which we integrate our boundary values, instead of this, one will always integrate with respect to the single measure which corresponds to a chosen reference point. In the unit disk model, this would be the measure corresponding just to the geometrical center of the unit disk. But then, of course, one has to compensate the fact that we are changing our measure, namely by adding the corresponding Radon-Nikodym derivative. So here, what happens is that Radon-Nikodym derivative is a function of three arguments, which are 2 points inside and one boundary point. Well, actually, here I'm writing it as a Radon-Nikodym cocycle, but it also has a very, very nice geometrical interpretation. It coincides with the so-called, well, its logarithm coincides with the so-called Buseman cocycle, but I don't really have time to talk about this, but I think Jean-François will mention that. Okay, so this is the Poisson formula. This is the Poisson formula for the hyperbolic plane. And now, so I have mentioned negatively curved manifolds, and now the probabilistic interpretation. The probabilistic interpretation is the following. So I remind you that here we are talking about harmonic functions. That's functions which are killed by the Laplace-Beltrami operator. Well, I should have Laplace operator of in the coordinate form. Or now, since I have switched to the geometric language, I have my negatively curved Riemannian manifold. I have the hyperbolic plane, and this Riemannian metric on this manifold determines the corresponding Laplace-Beltrami operator. So now I have to add the name of Beltrami to the name of Laplace. And then harmonic functions are, on a Riemannian manifold, other functions which are killed by the Laplace-Beltrami operator of the Riemannian metric. Now, from the probabilistic point of view, Riemannian manifolds are just diffusion operators on manifolds. And so this, the Laplace-Beltrami operator. And now we can consider the Laplace-Beltrami operator also as the generating operator of the corresponding diffusion process. The generator of the Brownian motion on the hyperbolic plane. On the hyperbolic plane. Okay, so now we have the local definition of harmonicity, but it can also be now reformulated in terms of the transition probabilities of our Brownian motion. So f, I always talk about bounded harmonic functions, so f is harmonic if and only if it satisfies the mean value property. The mean value property with respect to this diffusion process, with respect to the Brownian motion, namely the value of the harmonic function at point x always coincides with the expectation of its value, let's say, at time 1, for the Brownian motion issued at time 0 from the point x. Or here, actually, instead of 1, I can put any number t. So, once again, a bounded function is harmonic in the local sense, namely it is killed by the Laplace-Beltrami operator, if and only if it satisfies the mean value property with respect to the transition probabilities of the associated diffusion process. Okay, so now what is the interpretation of the harmonic measures in these probabilistic terms? The interpretation is also very natural. So now what happens? We have our hyperbolic plane, we have a certain point x, and we start our Brownian motion from this point x. Then one can show that the sample paths of the Brownian motion almost surely converge to the boundary. And therefore, one can look at the distribution of these boundary points, of these limit points, which is in probabilistic language often called the heating distribution. And of course, in this situation, when the curvature is constant, when we're talking about the hyperbolic plane, then here once again one can apply the symmetry considerations, and it's obvious that since the Riemannian metric is invariant with respect to all the isometries of our manifold, in particular with respect to all the rotations, all the isometries which fix this point, the corresponding heating distribution also has to be invariant with respect to all these rotations, and therefore these heating distributions are precisely the harmonic measures which I had described before. Okay, so that's the background. That's the background. And now what I'm going to do, I'm going to look at how, these representation formula so far, once again, the classical Poisson formula only works for the unit disk, or we can reinterpret it in terms of the hyperbolic plane, how it can be extended to a discrete situation, or carried over to the discrete situation. So the key property here is the following. We have to pass from an infinitesimal characterization of harmonic functions to their characterization in terms of the mean value property. So here actually there is a choice. For simplicity, I have written a characterization of harmonic functions in terms of the transition probabilities of the Brownian motion. However, it is more standard to describe harmonic functions by having the mean value property just with respect to just with respect to concentric balls or spheres. So anyway, I'm going to consider the following model. We are given a certain state space. I will always be talking about countable state spaces for simplicity, but in principle, this can be done for really an arbitrary state space. And then we have a map which assigns to any point from this step from this state space a probability measure on the state space. And then once we have such an assignment, of course, we can talk about the mean value property. So a function f will be called harmonic in the presence of such a structure. If it satisfies the mean value property, namely the value of our function at any point x will coincide with the result of its averaging with respect to the associated probability measure. And such an assignment naturally arises in geometric situations. For instance, if x is a graph, then one can consider for any point x the uniform distribution on the set of neighbors of x. Of course, presuming that the latter set, the set of neighbors, is finite, so I want the graph also to be locally finite. So, for instance, if we are talking about the square lattice, then if I choose a point x, then it has four neighbors. And the measure which I assign to the point x is just the uniform distribution on the set of these four neighbors. Namely, it gives weight 1/4 to each of these neighbors. And then what one obtains a certain class of functions, which be considered as an approximation of true harmonic functions. And actually, that's precisely what one does in numerical methods. You want to solve, if you want to find the harmonic function determined by its boundary data, if you want to solve seriously a problem numerically, then you apply one of the mesh methods, but they all amount to replacing the continuous state space with a certain graph, actually. And then what you do, you consider this notion of harmonicity, which was actually introduced, I think, sometime at the beginning of the 20th century, and it was studied under the name of pre-harmonic functions. Harmonic functions. So far I haven't said a single word about the probabilistic interpretation, but it's really begging to be said because, of course, this assignment, when we assign probability measures to points, provides us with what is called a Markov chain. So this is a class of random processes which was introduced by by Russian mathematician Andrei Andreevich Markov in 1905. So that's actually a certain dynamics, a certain dynamical model, which is very simple. So if we are talking about the classical dynamics, deterministic dynamics, then How does it develop? You are at a certain point, and then the dynamics tells you where you will be at the next point. I'm talking about discrete time, so x, tx. Then once you are at the point tx, you again apply your dynamics black box, and it tells you where you have to go at the next moment of time, t squared of x, and so on and so forth. Now, the Markov chain is very similar. The Markov chain is very similar. The Markov chain model is very similar. The difference is the following. Our dynamics black box is not deterministic anymore. So given a point x, what we have is not a single point, but instead we have a probability measure. We have a probability measure which can be thought of as a certain kind of cloud. There was a theory which was popular in the 60s and 70s, fuzzy mathematics, which consisted precisely in this. You replaced points with probability measures. It took a while to figure out that it was nothing but that. Yeah, so here instead of a single point, we have a certain cloud of points described by the distribution pi x, and we just sample one point from this distribution. And this will be our, let's say that was the starting point, x naught, and this will be our position at time 1. Then we have arrived at the point x1. Here, once again, we have a cloud of points associated with this point x1. We sample one point from this cloud, and this will become our point x2. And so on. So like this, we obtain a sequence of points, x0, x1, x2, and so on, which is, we can consider it as an orbit, as a trajectory of our dynamics. However, the difference with the deterministic model is that here our trajectory, our orbit is random, is a random sequence. Is a random sequence. Okay, so now let me consider two models, two simple examples rather, which are both described in terms of certain graphs. Here we are talking about this assignment which assigns to any point the uniform distribution on the set of neighbors. And in probabilistic terms, this, the Markov chain that we obtained is called the simple random walk. On a locally finite graph. Okay. So what is this simple random walk? Well, it's very popular among writers of popular literature. So they talk about a person who is not really, who doesn't really understand where he or she is and what she or he is doing. And so this person finds itself at a street corner and then doesn't know what to do, and then just finds a coin in the pocket, tosses the coin, and depending on the outcome, turns either left or right. So let me draw a slightly unusual street map. So this is a graph which is the homogeneous tree of degree. So each point has 4 neighbors. point has 4 neighbors, so that's T4. Homogeneous tree degree 4. And let's look at what happens if our random walker starts from a certain point. Let me denote the starting point by x. Okay, so here you see the situation is the following. Let's just look at the distance from the position of the random walker at time n and the original position. So then what happens is the following. Of course, if you are at the starting point, then the only way for the distance to change is to increase, right? So here the distance from x is 0, and no matter where you go, no matter which neighbors you choose, the distance will increase by 1. However, if you are at any other point, let's say here, then what you see is the following. You have 4 neighbors, but only one out of these 4 neighbors will be closer to the origin, right? So here the distance decreases by 1. Whereas if you choose any of the remaining 3 neighbors, the distance will increase by 1. The distance will increase by 1. So in other words, this distance also performs a Markov chain just on the positive integers. And what are the transition probabilities of this Markov chain? They're the following. So if you are at a point n, then you go to n plus 1 with the probability 3/4, to n minus 1 with the probability 1/4, and here, well, from the point 0, you just go to the point 1 with probability 1. And then, well, it's easy to see, well, here one can refer to the law of large numbers, for instance, that this random walk with this Markov chain, with these transition probabilities, happens to be transient, which means that our random walker will, the distance from the position of the random walker at time, at sufficiently large time, and the starting will go to infinity. So in terms of the random walk, of the simple random walk on this graph, it means that the distance between x0 and xn almost surely goes to infinity. Almost surely, which means for almost every sample path. Okay, so this is the statement in terms of the simple random walk on the graph, on the homogeneous tree. Okay, now this is a tree. This is a tree which has pretty serious consequences. So what does it mean? It means that actually there will be a certain stabilization in the way our random walker is located. Because here, this is a tree, which means the following. If we take an arbitrary point in the tree and want to join it with the point x, then we can only do it in a unique way. That's the definition of a tree. Which means that if you are, let me denote this point by xn. So if you are at a certain point on the tree, then you can look at the whole geodesic path, at the whole shortest path, joining this point xn with the starting point x0. Okay, and now what happens? Since this is a tree, look, if we are looking just at the situation near the chosen reference point, near the starting point of our random walk, then here we see that there are 4 different ways to proceed. Namely, our geodesics can either go this way, or that way. Okay, so that's something which actually subdivides all vertices of our tree into 4 subsets, right? And in order to switch from one of these subsets to another, one necessarily has to pass from this point. Because if we remove it, our tree will split into 4 connected components. Okay, so now here we know that the distance from our random walker to the origin goes to infinity. On the other hand, in order to switch from one component to another, one necessarily has to pass through the origin. Which means that we can only do it finitely many times, which means that in infinity, our random walker will forever remain in one of these 4 connected components. In other words, here we obtain a non-trivial behavior of our random walk at infinity. And of course, instead of talking just the branches obtained by specifying the first edge going out of our reference point, one can specify, for instance, 2 edges, and so on and so forth. So in fact, our tree is endowed with a whole boundary, in the same way as we were talking about the boundary of the hyperbolic plane. And then the fact that the distance goes to infinity alone in this situation implies that almost every sample path converges to a certain point of this boundary of the tree. So here the situation is completely analogous to the situation with the Brownian motion on the hyperbolic plane. We have a certain Markov process, we have a certain Markov chain, because time is discrete, so I call it Markov chain. And we know that the sample paths of this chain converge at infinity to a point of a certain boundary associated with our space. So what's the distribution of these hidden points? In the same way as we were dealing, as when we were dealing with the hyperbolic plane, here, since we have boundary convergence, we can ask a very legitimate question about what is distribution of the heating point. And here, once again, one can use symmetry considerations because everything here is very nice. And our tree has a lot of isometries. It has a lot of isometries, and in particular, it also has isometries which fix points inside. And then, since our random walk is determined in terms of the graph structure, it implies that the heating distribution also has to respect these symmetries. So the harmonic measure, the heating distribution, has to be invariant with respect to the group of isometries which fix our static reference point. So what is the distribution which we have obtained? In this situation, it can be described very explicitly. How does it look like? So we start from the point X. So here, once again, it's very important to realize that our state space from the very beginning doesn't have any reference points. So here, when talking about, when choosing a certain initial point, we are making an additional assumption. We are giving an additional structure to our space. Okay, so let's fix this initial point. So that's a vertex of the tree, and it has 4 neighbors. Okay, each of these neighbors, in turn, has 3 more neighbors, and so on. Okay, so now I said that the heating distribution has to respect the symmetries, the isometries. So what does it mean? Here we have 4 subsets of the boundary, which correspond to 4 first-order branches. And of course, there are isometries which exchange, which permute all these branches. And therefore, each of these branches must have the probability 1/4. In the same way, if we are talking about the second order branches, then we will have now how many? 12 of them. And again, the group of isometries will act transitively on these second order branches, and therefore each of them will have equal probability 1/12. So this explicitly describes our harmonic measure, because in this situation it happens to be the only measure on the boundary which is invariant with respect to all the isometries which fix the reference point. Why such a coincidence? Of course, that's not by accident. That's because our probabilistic structure, the transition probabilities, has been chosen in such a way that it is determined by a metric structure, by the neighborhood, how is it called, incident relation of the corresponding graph. Okay, so now let's go a bit further. Let's go a bit further and consider not just a single measure like this, but the whole family of the harmonic measures on the boundary. Well, it's easy to see that these harmonic measures are all pairwise equivalent. So once again, what is the description? We have our universe, which is the whole homogeneous tree, and then we pick a point as the center of this universe. And then we are kind of looking at the sky around us, and we take the measure the uniform with respect to our viewpoint, which is the point x. Now, if you look at the sky from a different point, then the distribution may change because your viewing angle will change. And therefore, you obtain a family of measures parameterized by the points inside. However, one can easily verify that these measures are still pairwise equivalent. One can, in this case, one can explicitly write down the Radon-Nikodym derivatives. That's just powers of number 3. I leave it as an exercise. And here, once again, because the transition probabilities had been chosen to respect the geometric structure, these Radon-Nikodym derivatives will admit a metric interpretation, namely the logarithms, once again, will coincide with the Boseman cocycle of the metric. Okay, so now what is important for us is that this family of measures, they have the following property. So suppose we are starting from our point x. Okay? Then we know that eventually we will hit the boundary. However, before hitting the boundary, one has to make the first step. And this first step is very explicit. We have to choose one of the 4 neighbors with equal probability. And then, this is the famous Markov property, our chain develops from each of these points chosen after the first step as if it didn't know anything about the origin. We just forget, that's a Markov property, we just forget about everything what happened before you found yourself at this point. So this means the following: if you have an arbitrary point x, then the associated heating measure will be just the average of the heating measures corresponding to the neighbors. So in this particular, let me write it more general. So the harmonic measure associated to the point mu x, x will be just equal to the result of averaging the harmonic measures of the points where we can get after the first step with respect to the distribution of this step, first step, and this distribution is just the transition probability. In this particular case, it just means that mu x will be equal to 1/4 of the sum of the measures of the harmonic measures corresponding to the neighbors. Okay, so we have this relation, and it looks, okay, there is something wrong here because, of course, I had to multiply them by the corresponding weights. Okay, so now what happens? This relation, it looks precisely like the harmonicity relation. That's a mean value property. And now let's take a boundary function. Let's take a boundary function and consider its integrals with respect to these heating measures. So as you can see, formally, as a formula, it looks precisely like the classical Poisson formula, the way I had written the hyperbolic plane. Then, since I have this stationarity relation, this mean value property for the heating distributions, then it implies that if the measures themselves satisfy this property, then the integrals with respect to these measures will also satisfy this property, and therefore this function is harmonic. Harmonic, so in this setup, harmonicity means that the function satisfies the mean value property. So here these angular brackets denote integration. So what is integration? That's a coupling of functions and measures. So that's precisely what I'm writing here. So the moral is the following. The moral is the following. For this graph, T4, we have a non-trivial behavior at infinity. We have this boundary convergence. And as a consequence, we have non-trivial bounded harmonic functions. And as one can easily see, in principle here I haven't really used much about the homogeneous tree, except for the following two facts. So first of all, I knew from some geometrical considerations that this homogeneous tree has a natural boundary, has a certain topological boundary, so that I can talk about limit points of my sample paths. And then I use the fact that the sample paths indeed converge to this geometric boundary. Okay? And then, in this situation, I can define the heating measures, and then by integrating boundary values with respect to these heating measures will give me non-trivial bounded harmonic functions. Now one can ask the following question. Given a general Markov chain, So what is a Markov chain? It's just assignment of transition probabilities. Then we have the notion of harmonic functions. Then the question is, are there non-constant harmonic functions? Non-constant, let me emphasize, bounded harmonic functions. Or, since in this situation in this model situation, in this example, I obtained non-constant bounded harmonic functions from non-trivial behavior at infinity, is there a non-trivial behavior at infinity? And of course, yet another question would be the following. So in this example, what did we do? We exhibited a non-trivial behavior at infinity, and then we noticed that the presence of a non-trivial behavior at infinity provides us with non-trivial bounded harmonic functions. Now one can ask the question, what is the relationship between these two properties? So let me give another example, very simple one. Suppose our state space now is the integer line. It is the integer line, and I want, in describing my transition probabilities, I want to use the geometric structure which is present on this integer line. So what I do here is the following. So I consider the associated Kelly graph, and then I consider the following Markov chain, which is also the simple random walk. So the transition probabilities from any point n to n plus 1 and n minus 1 will be equal just 1/2. Equal just 1/2. So what does harmonicity mean in this situation? That's a mean value property. So it means that the value of our function at any point n has to be equal to the half sum of its values at the neighbors. Or in other words, it means that I pass from the values of the function itself to its differences. It means the following, that the increment of the function has to be the same. The increment of the function has to be the same. So in other words, the values of this function have to form an arithmetic progression. And, well, one can put it in a fancy form. There is an explicit description of all arithmetic progressions, which shows that any arithmetic progression is either constant or it is unbounded, Since we were talking about bounded harmonic functions, conclusion is that here there are no bounded harmonic functions. No non-trivial, non-constant. No non-constant bounded harmonic functions. Because, of course, yeah, constants are always harmonic functions, because if you have a function which is identically 1, let's say, here you have 1 in the left-hand side and 1 in the right-hand side, because pi x are transition probabilities. Therefore, if you integrate function equal 1, you always obtain 1. So this property, absence of non-constant bounded harmonic functions, is actually also very well known in analysis, and it is called the Liouville property. Liouville property, that's a property that under within a certain, for certain situations when one can talk about, let's say, harmonic functions, then there are no non-constant bounded ones. Actually, although we call it the Liouville property and we ascribe the corresponding result about the analytic functions to Liouville, in fact, as it often happens, it was first proved by Cauchy several years earlier and even published. And moreover, Cauchy proved it as an application of his integral representation formula. He proved it actually in pretty much the modern generality. Well, if we are talking about analytic functions on the complex plane, whereas Liouville actually did it in a situation which from our modern point of view is entirely trivial, because Liouville established only the absence of doubly periodic non-constant analytic functions, which nowadays is completely obvious, let's say, from compactness considerations, because there are no non-constant bounded functions on compact sets because of the maximum principle. Anyway, this is what's called the Liouville property. This is what's called the Liouville property. And now what I'm going to, well, I don't think I will manage to finish it today, but what I want to begin is the following. I'm going to outline a construction of a certain space, which is called the Poisson boundary. Of a Markov chain. So the name of Poisson appears here because this is a boundary which will provide us with precisely the same integral representation formula for bounded harmonic functions as the one given by the classical Poisson formula. So let me once again write this formula. So the value of a function at a certain point x is equal to the integral of the associated function on the boundary with respect to the measure associated with the point x. So once again, formally, it will be precisely the same expression as the classical Poisson formula or as the formula which we had in the example of a tree. So how does one obtain this general representation formula? So the setup is the following. We have X is a countable state space. And we are given a Markov chain determined by its transition probabilities. So now I consider the space of bounded harmonic functions. That's a space of all functions such that their value at any point x is equal to the average taken with respect to the corresponding transition probabilities. So this is a subspace of L infinity of all bounded functions. So when do I finish? In 5 minutes, yeah? That's a space of all bounded harmonic functions. Bounded harmonic functions. And now the key observation which allows to define this Poisson boundary is the following. A function f is harmonic if and only if, when considered along sample paths of our Markov chain, it is a martingale. So what does it mean? So we have the space of sample paths. And in the usual way, since we are given the transition probabilities, for any initial point x, we can define the associated measure on the space of sample paths. That's probability measure on the space of sample paths issued from any point x. And more generally, one can also define the probability measure on the space of sample paths associated with an arbitrary initial distribution. Okay, and now if I'm given a harmonic function, or actually an arbitrary function on the state space, then we can consider the associated function, or rather family of functions on the path space. So for any natural n, I put fn of x bar. So x bar is a sample path, boldface x. And I define the value of the n functions on my sample path to be just the value of the function f at the point xn. So I'm just looking at the values of my function f along a sample path, and it provides me a family of functions on the space of sample paths. And now the key observation is that a function f is harmonic if and only if is family of functions fn is a martingale with respect to the natural increasing filtration of the coordinate sigma algebra. Okay, let me denote by A0n the sigma algebra generated by the positions of my random walk at times between 0 and n. So this is an increasing family of sigma algebras. And my claim is that harmonicity is equivalent to this sequence in a martingale with respect to the coordinate sigma algebras. Okay, so now it's the time to stop today. So tomorrow I will start from, I will explain why indeed this is the case, and then we'll use it in order to construct the Poisson boundary.